So first series we talked about was a geometric series, something like 1 over 3 to the n, which was 1 plus a third plus a ninth plus a 27th, et cetera, et cetera, et cetera. Okay? And we realized, and you can see this either looking at the terms, that you're multiplying each term by a third to get the next term. And that's one way to figure out that r is less than 1. Another way of writing down what r is you took the next term and divided it by the previous term, right? Okay. And as long as r, which is a to the n plus 1 over a to the n, the absolute value of it is less than 1, then we said the geometric series converges. Okay? Well, the ratio test is pretty much that, only it just enables you to look at certain series that cannot be expressed geometrically, but to be able to evaluate their convergence or their divergence by looking at this ratio. It converges. The only time you can say it possibly converges is if their terms trend towards 0. But like 1 over n, that series does not converge. So it's only as the terms trend towards 0, that's when we say possibly converge. For a geometric series, we definitely converge if you know r is less than 1. Right? Okay. Well, for any series, so long as a to the n trends towards 0, for any series, if we look at a to the n plus 1 over a to the n, and if this ratio is less than 1, the series will absolutely converge. However, we're not going to just look at two random terms. We need to look at, the terms as we trend towards infinity. So I can't look at like my third term and divide it by my second term. And if I say, oh, that's less than 1, that means my entire series converges. We need to look like at every term. Okay. Now, similar to a geometric series, if it is greater than 1, the series diverges. However, one part where the geometric series differs from this ratio test is if we equal 1, we may converge or diverge. We need to evaluate and look into things a little bit more. Investigate more. Okay. Now we're going to be looking at some series with factorials in them. Okay. 2 to the n over n factorial, or 5 to the n over n factorial. Okay. Let's just remember factorials. It's just the integers all the way down to 1 being multiplied by each other. We'll be dealing with expressing just random n factorials, and we can write it as n times n minus 1 times n minus 2, all the way till we get down to 1. If I have n plus 1 factorial, well, I'd start with n plus 1, and then the next term would be n plus 1 minus 1, which is just n. And then I'd have n minus 1, n minus 2. all the way down. Well, that's the exact same as n plus 1 times n factorial. If I have like 2n, you can write it as 2n times 2n minus 1 times 2n minus 2 all the way down to 1. Well, if I have 2n plus 1, I would first rewrite this as 2n plus 2 factorial. And I'd say, okay, that's 2n plus 2 times 2n plus 1 times 2n plus 0, or 2n times 2n minus 1, 2n minus 2. That's just the same as 2n factorial. So I kind of went straight to this answer here. Now, let's look at the growth of n in terms of like n factorial or x factorial. We discussed back in the days and when we first started this unit, reminded ourselves that numbers don't grow. The log function, and we'll say the log of n, is the slowest growing function. It's slower than n to a power, which is slower than a number to the n power. The question is, where does n factorial fit in this growth chart? Discuss it with your neighbor. Where do you think that n factorial fits in? All right, did anybody say it was the slowest growing function? All right, good. Did anybody say it was the fastest growing function? You guys are correct. Darn it! All right, well, I mean, you think about like 10 factorial, and you get 3,628,800. And it's like, okay, that's pretty big. But like compared to like 10 to the 10th. Okay, so 10 being my number, or let's just do 9. 9 as my number to the 10th power. And, you know, all of a sudden we're already close, but this is bigger. But then if I go to 9 to the 100th, okay, I'm multiplying 9 by itself 100 times. I get this 96 digit number, okay? 9 times itself 100 times. Well, think about 100 factorial. We are multiplying 100 numbers together. But like 90 of them are bigger than 9. So we'll see that 100 factorial is definitely bigger than 9 to the 100th. This is 158 digits long compared to 9 to the 100th, which is 96 digits long. Okay? No matter how big the number is to the x power, you know, even if you put like 9 million to the x power, eventually with factorials, you'll get a bigger enough number that the numbers you're multiplying are bigger than that original number, and it will compensate for the numbers that are less than. So, turns out, those of you who raised your hand were correct. N factorial is faster than a number to the nth power. What would be faster than n factorial? N to the n. Think about 100 to the 100. It's 100 times 100. 100 times. Well, that's bigger than 100 times 99 times 98 times 97. Okay? So, n factorial wins. Which means if I asked you about this sum of n factorial over 5 to the n, because you know n factorial is faster growing than 5 to the n, slower growing, and that this limit approaches infinity, you know this is definitely divergent by the nth term test. Okay? But what if I flipped it? What if I had 5 to the n over n factorial? Are we convergent or divergent? Let's assume this is 5 to the n over n factorial. Well, it's not a p-series, so I can't use a p-series test. It's not a limit I can compare to anything that I know, so I can't use the direct comparison test. It's not a geometric series, so I can't use that test. What do I have to use? I have to use the ratio test. Okay? Ratio test, once again, is, if we look at the n plus 1th term, and I divide it by the nth term, if this ratio is less than 1, we're convergent. Well, let's make sure we can express the n plus 1th term. Instead of n's, I'm going to replace them with n plus 1s. So this is 5 to the n plus 1, and this is n plus 1 factorial. Use parentheses when you are plugging in n plus 1. All right, well, I will look at the limit as n approaches infinity of the absolute value of 5 to the n plus 1 over n plus 1 factorial over 5 to the n over n factorial. And I'm going to get that value, and if it's less than 1, I win. Well, I don't like these fractions over fractions, so what I will do is instead of doing a to the n plus 1 over a to the n, I'll just write this as a to the n plus 1 times 1 over a to the n. So just a flipped a to the n fraction. So instead of writing this, I'm going to, and starting from now, whenever we do this, I'm going to just skip this step and go straight to 5 to the n plus 1. Oops, the n plus 1 is in the exponent. 5 to the n plus 1 over n plus 1 factorial times n factorial over 5 to the n. Okay? All right. Now, what I'm going to do is rewrite some terms and simplify some things by moving things to be kind of with their like term. So let's start by moving some things so they're with their kind of partners. So I'm going to move 5 to the n underneath 5 to the n plus 1. And I'm going to move the n plus 1 factorial underneath the n factorial. And then I'm going to try to simplify this because I'm trying to find the limit as n approaches infinity. I don't know what the limit of this is. Okay, so I'm going to simplify. I'm going to rewrite 5 to the n plus 1 as 5 to the n times 5. I'm going to leave n factorial as it is. I'm not going to write it as n times n minus 1 times n minus 2. And I don't write it that way because I know that n plus 1 factorial in the denominator is n plus 1 times n factorial. N plus 1 times n minus 1 times n minus 2, on and on and on. So I'm just going to write n factorial over n plus 1 times n factorial. Now we are finding the limit as n approaches infinity of this. And now I can simplify this. And I get the limit as n approaches infinity of the absolute value of 5 over n plus 1. Now, a lot of times students get to this spot and they're like, I don't know what to do now. But remember, this is what our goal is. Our goal is to find the limit as n approaches infinity. All of the simplification, all it's being used to do is to find that. So, evaluate the limit. Plug in infinity for n. What does this trend towards? 0, which is less than 1, which means the series converges. Okay? Let's do a second one, then we'll move on. I'll come back to a future one. This one does not have a factorial, but it's 2 to the n. We have not talked about, we've talked about this in terms of a geometric series, but it was a constant to the n power. Here I have n cubed over 2 to the n, so it can't be compared directly to a geometric series. It could be, but it would not produce a comparison that would give us a definitive answer. So in this situation, I'd use the ratio test. And the ratio test could be used for everything. So let's find the limit as n approaches infinity of a to the n plus 1 times 1 over a to the n and let's see what that is. If it's less than 1, we win. We can go through and do 2 steps at once. I can have the n plus 1 being cubed over the n cubed. And then I can have the 2 to the n over. I can rewrite 2 to the n plus 1 as 2 to the n times 2. The 2 to the n's cancel. Giving me limit as n approaches infinity of n plus 1 cubed over n cubed times a half. Now people try to simplify this, but actually I don't want to simplify this. I'm ready to take the limit as n approaches infinity. Now if I plug in infinity here, I get infinity over infinity. That doesn't get you an answer that you should like. But instead you think about the relative growth of things by looking at their highest agreed or the fastest growing terms. You can rewrite n plus 1 cubed as n cubed plus other stuff that will grow slower than n cubed. That other stuff is insignificant compared to the growth of n cubed. So this here, as n approaches infinity, this approaches 1. Which means this limit equals 1/2, which is less than 1, which means the series converges. Okay, I'll come back and do this in the video, in that one, and let's move on to a power series. Okay, we've dealt with power series before, but a power series is just a series with a variable in it. We'll be using power series a lot next unit. Okay, an example, this power series, if n starts at 0, remember 0 factorial is 1, x to the 0 is 1, so I have 1 plus, this would be x to the first over 1 factorial. This would be x squared over 2 factorial, x cubed over 3 factorial. Okay, so that's a power series. Now we have had problems so far in this unit talking about the convergence of some of these power series. Okay, we've done problems with geometric series and with p-series asking us, hey, find this x value so that the series converges. And for a geometric series, all you care about is the absolute value of r being less than 1. So you would take this inside 2x minus 1 over 3. The absolute value of that, make sure it's less than 1. That gives you an equation 2x minus 1 over 3 is less than 1 and greater than negative 1. Multiply both sides by 3, you get 2x minus 1 is less than 3 and greater than negative 3. And you can add 1, multiply by 2, you get x is less than 2 and greater than negative 1. Okay, we did that. That's not new. For P series, we know that P has to be bigger than 1, not less than 1. So I would look at 3x minus 1, make sure it's bigger than 1. That's when 3x is bigger than 2, or an x is bigger than 2/3. Okay, we've done that before. Well, now we are going to have to do the same with these power series, where we can't see and we don't know and we can't rewrite it as a geometric series or as a P series. This is just some other type of series. And I got to figure out the x values that guarantees the convergence of this series. Okay? We're going to have to use the ratio test to set up an inequality. So we're going to have to say, okay, well, this is going to converge when the limit as n approaches infinity of a to the n plus 1 over a to the n, when that's less than 1. Okay, here we go. Now, since I'm taking an absolute value, we can disregard any alternating signs. I would just have the limit as n approaches infinity of the absolute value of x minus 2 to the n plus 1 over n plus 1, 5 to the n plus 1, times the reciprocal of an, 5 to the n times n, over x minus 2 to the n. This must be less than 1 for my series to converge. Okay, next step. We will make sure that we can simplify this, write it with its kind of partners, and try to simplify it as much as possible. Okay, so I will rewrite x minus 2 to the n plus 1 as x minus 2 to the n times x minus 2. I will put that over x minus 2 to the n, which was in this denominator. I'm going to put the n over the n plus 1. I'm not going to simplify anything there. Can't. And then I have the 5 to the n over 5 to the n plus 1, which is 5 to the n times 5. This absolute value must be less than 1 for our series to converge. Well, let's see. The x minus 2 to the n's will cancel. The 5 to the n's will cancel. But let's look at this. What cancels here? Nothing cancels. But we are finding a limit as n approaches infinity. As n approaches infinity, this approaches 1. The plus 1 won't matter. You just have n over n, which is 1. Okay, so knowing that, I have evaluated my limit. I got rid of everything with n's, and I know this approaches 1. I have this inequality with an absolute value set up. X minus 2 over 5 has to be less than 1. I can solve this. We've solved these with geometric series. Okay, leave some space though, because we're going to do more with this problem. Start with x minus 2 over 5 is between 1 and negative 1. Multiply by 5. Add 2. So I got x is less than 7, and x is greater than negative 3. Okay, this appears to be my answer for all of my x's But wait, there's more. Before we get to the more, let's talk about what it means to, if you're asked for the radius of convergence. The radius of convergence is, the distance from the center of your interval of convergence to the endpoints. So, if you have from -3 to 7, the middle of that is 2, and the radius is 5. Okay, it's the distance from the middle of your interval to the endpoints. Middle of your convergence interval to the endpoints. Some locations where you can see the 5, this first step here, you see this 5, if you multiply both sides by 5, you actually can do that and have the absolute value of x minus 2 less than 5, so that shows up here. It shows up when you multiply by 5 here, and you have -5 x minus 2, 5. So different ways to see the radius of convergence within your answers. Okay? But I said, wait, there's more. There is. Upon closer examine of the ratio test, the ratio test said that if this R is less than 1, the series absolutely converges. Okay? But when R equals 1, the series may converge. It may diverge. So we actually need to do some more examination of when this ratio equals 1. So let's go back over here and figure out, when did this ratio equal 1? Well, if I just turn this into an equal symbol, we'd see at -3 and at 7, we equaled 1. So at those two endpoints, we have this situation where we have an inconclusive ratio test, and we need to do further examination. Okay? So, after careful examination of the ratio test, we see that we need to inspect further when a to the n plus 1 over a to the n equals 1, which occur at our endpoints of our interval. So, going back up to the same problem, we're going to call this checking our endpoints. And we will find that these endpoints will be locations of possible conditional convergence. Because if you're less than 1, you're absolutely convergent. But conditional convergence is still convergence. Okay? All right, so when x is, let's start with 7. When x is 7, we are going to plug in 7 into your series for x. So using the series from above here, you plug in 7 for x, and you rewrite it out. I get the sum, n starts from 1 to infinity, of -1 to the n times 7 minus 2, which is 5 to the n, over n times 5 to the n. Okay? We don't have a power series anymore. We just have a regular series. Let's look at it. Well, the 5 to the n's can actually cancel, so I don't need that. And this simplifies to just be the sum n starts from 1 to infinity of negative 1 to the n over n. I know that it's that is the alternating harmonic series that is convergent. So actually, when x equals 7, we are convergent. I then come back here and change that from a less than symbol to then a less than or equal to symbol. I need to check when x equals negative 3. I get the sum, n starts from 1, goes to infinity, of negative 1 to the n times negative 5 to the n over n times 5 to the n. Now, I can't just cancel these negative 5 to the n's with this 5 to the n. But I could if I rewrote this as negative 1 times 5. Since it's a product, I can distribute the power. So it's negative 1 to the n times 5 to the n. The 5 to the n's can now cancel, but I have negative 1 to the n times negative 1 to the n. What do you think that is? Always going to be 1. It's like negative 1 to the n squared. Something squared is always going to be positive. It'll always be positive 1. So this simplifies to be the sum n starts from 1 goes to infinity of 1 over n. We know that this is the harmonic series and it's divergent. So after all that, that is my final answer. That series will converge when x is less than or equal to 7 and greater than negative 3. These are involved problems. You need to practice them. I'm going to go back and do a couple more ratio tests and then do the rest of the power series. You can watch these in the video. And make sure you do your quiz to practice. All right, we'll start with this regular series. We want to see if it converges or diverges. And let's use a ratio test. Remember, use parentheses when you plug in n plus 1. Then rewrite, simplify. This 2 times n plus 1 factorial turns into 2n plus 2, which turns into 2n plus 2 times 2n plus 1 times 2n factorial. We cancel. I'll have the limit as n approaches infinity of n plus 1 squared over n squared times 1 over 2n plus 2 times 2n plus 1. As n approaches infinity, this will approach 1. I'll just have n squared plus some extra stuff over n squared. The growth of the n squareds dominate the growth of the other terms. as n approaches infinity, this will approach 0. I have 1 over infinity. So I have 1 times 0, which gives me a ratio that equals 0. That is less than 1. The series converges. Most of these that I do show convergence. There will be some where the limit approaches infinity. Usually when that occurs, you'll see that the nth term test fails. So you don't, make sure you check the nth term test before you start going in through the ratio test. Yes, but that's a lot of work to discover that your terms aren't trending towards 0. All right? Let's see if this guy converges. 2 to the 4n. It's got a negative 1 to the n. Let's say we don't know that these terms will decrease at all times. We do see it's an alternating series. Since I know it's an alternating series, I can almost let me just do this problem without that fact. Okay, with an alternating series, we know alternating series converge if the terms decrease. This will grow faster than this, so yeah, it's going to decrease. Anyways, let's go and use the ratio test. This turns into the limit as n approaches infinity of 2. This is 4n plus 4. So it's 2 to the 4n times 2 to the 4th. I'll write that over 2 to the 4n times, this is 2n plus 2 plus 1, which is 2n plus 3. So I'm going to leave this as 2n plus 1 factorial. And I'm going to write the denominator, which is 2n plus 3 factorial, as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. Cancel, 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 cancel. If I look at the limit as n approaches infinity of 2 to the 4th over 2n plus 3 times 2n plus 2, I know this will trend towards 0. That 0 is less than 1, so the series converges as well. Okay? So, examples of using the ratio test. On your quiz, you'll see some will not converge. Let's look at more power series where we need to check our endpoints, because that's the locations where the n plus first term divided by the nth term will equal 1. Okay, let's look at this guy. When will this converge? Well, I'm going to look at the limit as n approaches infinity of the absolute value. Since the absolute value is there, I can just disregard this. Worry about it at the end. Don't erase it or anything. All right. So I have x minus 1 to the n plus 1 plus 1 over 2, in parentheses, n plus 1 plus 1. Then that's times 2n plus 1 over x minus 1 to the n plus 1. This needs to be less than 1. I have x minus 1 to the n plus 2. So that could be x minus 1 to the n times x minus 1 squared. that is over x minus 1 to the n times x minus 1 from this guy. And I have 2n plus 1 over 2n plus 2 plus 1, which is 2n plus 3. This needs to be less than 1. X minus 1 to the n cancel. One of these cancels with one of these. You can't simplify this, but as n approaches infinity, this guy also approaches 1, giving me the evaluated limit, which is the absolute value of x minus 1, has to be less than 1. That gives me the equation x minus 1 has to be between negative 1 and 1. Sees my radius of convergence is 1. I add 1. X has to be less than 2 and greater than 0 for absolute convergence. We have to test when the ratio equals 1, which will be at our endpoints. And to do that, we plug our endpoints into the original function. Let's keep that there. That's fine. Okay. So let's check for conditional convergence. Start with x equals 2. I'll have negative 1 to the n plus 1 times 1 to the n plus 1 over 2n plus 1. Okay, well, 1 to the n plus 1 is just going to be 1. So this simplifies to be the sum n starts from 1 to infinity of negative 1 to the n plus 1 over 2n plus 1. This is a convergent series that could be, that's an alternating series. It can be compared to the harmonic series. If I check x equals 0, we start at 1, go to infinity. Again, we have that negative 1 to the n plus 1. We'd end up having another negative 1 to the n plus 1 over 2n plus 1. Well, these are just negative 1 to the n plus 1 squared. It'll just give us a positive 1. Now this is a divergence. You can do a comparison, a limit comparison with the harmonic. And if you were to do these problems on a free response portion of a test, you'd have to show the comparison. So x equals 2, we were convergent, so that gets included in our interval. X equals 0, we are not. Let's look at this one, x to the n over n factorial. Going to go straight to the second step where I have n plus 1 times 1 over a sub n. The n plus 1 would be in the denominator here for the factorial. And then we know this is the limit as n approaches infinity of x to the n times x over x to the n. And then n factorial, I'll leave. This changes to n plus 1 times n factorial. Cancel, 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 cancel. I have the limit as n approaches infinity of x over n plus 1. This has to be less than 1. This is a good question because when we get here, a lot of people like to just ignore this n plus 1 and say, okay, x has to be less than 1. But it's not the case. If I look at this limit as n approaches infinity, no matter what x is, this approaches 0. So we have a situation where we have just 0 is less than 1. Well, that's true. What does that mean? That this series actually converges for every single x value. Okay? So it turns out this n factorial grows so much faster than x to the n that it doesn't matter what number's up here. Our terms will trend towards 0 fast enough that our series will converge. Let's do another one. I'd like to do this one, but without the negative 1 to the n. So I'm going to remove the negative 1 to the n. Just have 1 over 2 to the n times x plus 3 halves to the n. And this is a great example of, like, you don't have to use the ratio test if you don't really want to. Because I could write this as x plus 3 halves over 2, this quantity to the nth power, and all of a sudden we have a geometric series. We'll end up with an answer that is the exact same thing as if we use the ratio test. But the geometric series is a lot quicker to do, because we already know that it's, okay, x plus 3 halves over 2, this absolute value is less than 1. That's what we're going to end up with anyways using the ratio test, but watch how much longer it takes to get there. All right, here we go. Limit as n approaches infinity of 1 over 2 to the n plus 1. We'd end up with a 2 to the n in the numerator. Absolute value. We got x plus 3 to the n plus 1 over x plus 3 to the n. This has to be less than 1. All right, well, I'm going to rewrite it as 2 to the n over 2 to the n times 2 times x plus 3 to the n times x plus 3 over x plus 3 to the n. That has to be less than 1. This cancels, 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 and look at what we have. It's actually not the exact same. Oh, because it should be 3 halves. Never mind, it is the same. We end up with the limit as n approaches infinity. There's no more n's to deal with, so the limit is done. We just completed the limit. We have x plus 3 halves over 2 has to be less than 1. Boom. We can tell just right away that the interval of convergence is going to be 2. Will have to be between -2 and 2. So here, x plus 3 halves would be centered at 0, but I can add 3 halves. So 7 halves and oops. -1/2. Time to check your endpoints for conditional convergence. If I plug in 7 halves, I get sum, n starts at 1, goes to infinity, of 1 over 2 to the n, times 7 halves plus 3 halves is 10 halves. 10 halves is just 5 to the n. feel like I did a mistake here. 4, 5, 6, 7 halves. No. Okay. 5 halves over 2 halves. That is definitely a divergent geometric series. Oh, gosh, I did make a mistake. I knew it. This is 4 halves minus 3 halves. I have to subtract 3 halves. So this is going to be 1 half. And then this is minus 4 halves. This is negative 7 halves. All right, good. So when x is negative 7 halves, negative 7 halves minus 3 halves is minus 4 halves, which is minus 2 to the n. And if I look at this further, I could rewrite this as negative 1 to the n over 2 to the n over 2 to the n, which cancels. We know that the sum of negative 1 to the n is divergent. You can use the nth term test. The terms don't trend towards 0. If I look at x equals 1 half, we have the sum, n starts from 1, goes to infinity, of 1 over 2 to the n times this would end up being 2 to the n, which is just 1 to the n, which again is divergent because the nth term test. Okay, very involved doing all of that just to get this answer. If we recognize this was a geometric series, well, the geometric series test does not provide for this inconclusivity on our endpoints. We would just have x plus 3 halves over 2 has to be, absolute value has to be less than 1 for a geometric series to converge. Okay, so I don't have to check my endpoints if I recognize that I could use the geometric series test and not the ratio test. Okay. Now, let's see one where we have a square in our absolute value. So I have x minus 3 to the 2n over n. I feel like this will never be convergent. Let's find out. And it's because it's like the harmonic series in the denominator. So it doesn't matter what's in our numerator. So let's see. Now, using parentheses, it's x minus 3 to the 2, n plus 1. So that's 2n plus 2. That'll be over x minus 3 to the 2n. This is times n plus 1 over n. This has to be less than 1. The limit as n approaches infinity of, this is 2n plus 2. So this is x minus 3 to the 2n times x minus 3 squared. The denominator will have x minus 3 to the 2n. And here, n plus 1 over n, this absolute value has to be less than 1. I can't simplify this, but I can take the limit as n approaches infinity of this, and this approaches 1. These cancel, leaving me with just x minus 3 squared has to be less than 1. Okay, well, I can do that. Now, what we want to do in this situation is understand that if you take a square root now, it's not going to change the absolute value. Okay, because we'll always get a positive value here. So I don't want to rewrite this as x minus 3 squared and then take a square root of this negative. That's not going to help me out at all. Instead, we're going to square root in this step because it's after this step that we can then say, and of course the root of 1 is just 1, we can write this as x minus 3 is between 1 and negative 1. And our radius is 1. X is between 4 and 2. Okay? So make sure we do that. We square root here, not at the next step where we have the negative 1, because then we'd have a square root of a negative number. I'm going to check my endpoints. I feel like, oh, there's why. Why is 2 to 4 going to work? Well, 2 to 3 would give us an alternating series, because then this would have a negative. And then 3 to 4 would give us a small enough value to the 2n that would increase the growth of our denominator. It could be a fraction to the n. So that's why. It's not just going to never be convergent. So we're going to check our endpoints when x is 2. And I have the sum, n starts at 1, goes to infinity, of, I plug in 2 in for x, I have negative 1 to the 2n over n. Now, negative 1 to the 2n can be written as negative 1 squared to the n, which is just 1 over n. And this series is a divergent harmonic. I mean, all harmonics are divergent, so it's divergent because it's the harmonic. And if we look at x equals 4, we'd end up with positive 1 to the 2n over n, which is just 1 over n, which again is a divergent harmonic. So this is our answer here. Okay. One more. Last one's very short. Limit as n approaches infinity of x minus 4 to the absolute value of 2 to the n plus 1. That's 2n plus 2. Not 2n plus 1. And I'd have x minus 4 to the 2n. And I have 3 to the n in the numerator and 3 to the n plus 1 in the denominator. That has to be less than 1. Rewrite it as x minus 4 to the 2n times x minus 4 squared over x minus 4 to the 2n times 3 to the n over 3 to the n times 3. That has to be less than 1. Cancel, 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 cancel. We have this. Limit as n approaches infinity. Don't have any n's. So we've just evaluated the limit. The absolute value of x minus 4 squared over 3. That has to be less than 1. Now, before I get rid of the square, I can't square root both sides right now, or else I have a root 3 in the bottom. I'm going to get rid of the 3. This turns into x minus 4 squared is less than 3. I can get rid of a constant like that in this inequality using an absolute value, understanding that this is a positive value and it's not going to affect things. When I take the square root of both sides, now I get x minus 4 is less than root 3 and bigger than negative root 3. And then add 4 to both sides. X is less than 4 plus root 3 and bigger than 4 minus root 3. Okay, radius is root 3, centered at 4. Okay, let's see what happens if I plug in 4 plus root 3 and 4 minus root 3. I'm going to check my endpoints. I'm going to go ahead and grab my series again, just so I can see it quickly. Great job. Okay, so there's my series that I'm trying to evaluate right here. I'm going to check when x is 4 plus root 3. Doesn't matter which order you check them. You have the sum, n starts at 0, goes to infinity, of 4 plus root 3 minus 4 to the 2n over 3 to the n. 4's will cancel. Root 3 to the 2n can be written as root 3 squared to the n, which is just 3 to the n over 3 to the n. Cancel, cancel, 1. Sum of 1's, divergent. Then, 4 minus root 3. Four minus 4 goes away. Again, the negative root 3 to the 2n can be written as negative root 3 squared to the n over 3 to the n. That will cancel to be just 1 and is divergent as well. So we end up with the squares eliminate the possible endpoint convergence. Okay, but all the values in between those would converge. Finally, we have a question. The series below converges conditionally at 5. What can we say about the series at 2, 0, and 1? All right, well, we could see that if x equals 3, okay, and with all these, if we talk about a value that produces a 0, if this turns into 0, well, if you take a sum of anything that is 0, you know that we're going to have a converging sum. The sum of 0 and starts at 1 goes to infinity is 0. It's convergent. Okay? So the center will always be the x value that will give us a 0. Okay? Here we centered at 1. Here we centered at 0. And it was convergent everywhere. Here we centered at negative 3/2. Okay? So keeping that in mind, we know that this is the center of convergence. Now, talking about the ratio test, we know that if you have your center at 3 and at 5 we had conditional convergence, well, everywhere in between is going to be absolute convergence. Which means we have a radius of 2. Or if I go down 2 to x equals 1, well then I have another endpoint where I could possibly converge. So if they ask you, what does this tell you about the series at x equals 2? Well, 2 falls in my radius of convergence, so we will definitely converge. We will absolutely converge. X equals 0 will definitely be outside my radius, so we're definitely going to diverge. And x equals 1, I don't know. I could plug in 1, I get negative 2 to the n. Well, it's all dependent on what a to the n is. Maybe it also is negative 2 to the n. So maybe you'd have like a positive 2 to the n. And then you have just a harmonic series. It's all dependent. So that's the ratio test. Involved stuff.